Welcome to our physics lesson today. Our topic today is Newton's laws of motion. Newton's laws of motion. The Newton's laws of motion. And in our discussion today, we are going to look at the other law of motion, which is the Newton's third law of motion. The Newton's third law of motion, which is our last law. We have been looking at the first law, the second law. In the previous lesson, we looked at impulse. We got the relationship between impulse and momentum, whereby we said it is equal to the change in momentum. And we say that the impulse is given by the product of force and time. We get the impulse. And we also say that the SI unit of impulse is Newton second. And therefore, we also say that another unit for momentum is Newton second. So I'd like us to look at the Newton's third law of motion. And I would like us to consider the following. Consider the following. Here I have a mass, or we can talk of a block, which is placed on a bench. Let's say this is our bench. We have it that way. And then here we have a block, a wooden block. This is the block that we have. This is the block. And it is resting on the bench. It's resting on the bench. And when it rests on this bench, it is not in motion, it is at rest. When it rests on this bench, we are going to find that this block will exert some force on the bench. And it will exert some force. If this is the center, we are going to have it exerting some weight. Here we are going to have the weight being exerted on the bench, weight W, and weight is given by mass multiplied by the gravitational force, because this body will experience some gravitational force. So there will be a force that is exerted on the bench, and in return, the bench will also exert some force on the block. So there will also be another force which will be opposite but equal. It will also exert some other force on the block. So the block is exerting some force on the bench, and in return the bench is exerting some force on the block. And this force, we refer to it as the reaction. This is the reaction force. And this force that is exerted by the block on the bench, we refer to it as the action force. Whereas the other one we have as the reaction force. And therefore we say that whenever there is an action force, there is an equal and opposite reaction force. So for the Newton's third law of motion, we say that for every action, there is an equal and opposite reaction. And that is the Newton's third law of motion. So Newton's third law of motion, Newton's third law of motion, the Newton's third law of motion states that for every action, it states that for every action there is an equal and opposite. There is an equal and opposite. There is an equal and opposite reaction. So that is the Newton's third law of motion. That when this block is placed here on the bench, it will exert some force. And the bench again in return will exert some other force on the block. And these forces are equal, but they act in different directions. So we have in opposite directions. So we have the weight acting on this direction, the reaction is acting on the opposite direction. And therefore, for every action, there is an equal and opposite reaction. And that is what we refer to as the Newton's third law of motion. And with this, we are going to now look at various formulas for calculating the resultant force for a body that is in a lift. So we are going to look at the weight of a body in a lift. The weight of a body, the weight of a body in a lift. The weight of a body in a lift. A lift is also called the elevator. The elevator. So the weight of a body in an elevator. So we are going to consider one case whereby when the lift is at rest, when it has not started moving. Again, when the lift is ascending, when it is moving upwards with an acceleration A. And then again when it is moving downwards with an acceleration A. So we are going to look at the weight. What is the resultant force? So the weight of a body in a lift or an elevator. So we should know that whenever you are using a lift or whenever a passenger gets into a lift, there is a force that presses against the foot of the passenger, and that force depends on 1, the acceleration, and 2, the direction of motion. Is it upward or is it downward? So we can say that a passenger is that person who is using the lift. A passenger in a lift experiences a pressing force against the feet. Depending on one, we have seen the direction of motion, on the direction of motion, and number 2, depending on the acceleration of that lift. So we'll have the pressing force. So the pressing force is not the same for a body that is moving downwards and another one that is moving upwards. That is for the lift that is moving upwards and another one that is moving downwards. So we are saying that a passenger in a lift will experience a pressing force against the feet depending on the direction of motion and also depending on the acceleration. So I'd like us to consider here a body. We have now a body of mass M which is weighing on a lift. And we are first going to consider a passenger. Consider a passenger of mass M. Passenger of mass M in a lift. And we are going to look at now the 3 cases whereby 1, we are going to consider the weight of a body, the weight that is when the lift is at rest. So we start with the first case when the lift is at rest. Lift at rest. We get to know what will be the reading on the scale. If we have a scale in the lift, for example, this is what we mean. Let's say this is our lift. This is the lift. And then we are having a scale. And we want to know what will be the reading on the scale when the lift is at rest. So here we have our scale. Let's say this is our scale here. This is the scale. And then here we have the person who is using this lift. So we have the person here using the lift. The person using the lift. So we have the scale here. So this is when the lift is at rest. When the lift is at rest, remember this body is not in motion, and therefore we'll have the weight acting on this lift, we'll have the weight of the body. Here we have the weight of the body, which is given by mass times the gravitational force acting on this lift. And again, from the Newton's third law of motion, we have seen that for every action there is an equal and opposite reaction. So again, we are going to have an opposite force, that is the reaction. So we'll have our reaction force there. And therefore, when this lift is at rest, it simply means when it is at rest, when we want to get the resultant force, when it is at rest, we simply have to show that it is at rest. We have, when we add this force, the downward force, mg, we add the upward force. The upward force is the reaction force, which is now on the opposite direction, so it is negative mg. So we have plus negative mg, we get that is equal to 0. And therefore, that shows that the lift is at rest. And therefore, the scale, this scale that we have here, the reading on the scale, will simply be equal to the weight of that body, the weight of the body. And therefore, the reading on the scale will simply be equal to the weight of the body, which is given by the mass times the gravitational force. So that will be the reading on the scale when the lift is at rest. When the lift is at rest, I want us to move ahead and consider another case now when the lift is moving upwards. When the lift is moving upwards with an acceleration a. When the lift is moving upwards, so we have number 2, lift moving upwards with acceleration, with an acceleration a, the acceleration is there. So the lift now is moving upwards. I want us to consider this case and again get the formula for the reading on the scale. So we consider again, here we have a lift. In this case, the motion is upwards. So we have our lift. Let's say that's our lift. And then we have the scale here. This is our scale. And this is what we have. This is our scale. And we have the passenger who is using this lift. So we have the passenger here who is using the lift. And we have seen that it's moving upwards with an acceleration a. So that is the acceleration. So in our case here, our acceleration is positive. Our acceleration is positive. Now, in this case, we have the following, and we want now to get the reading on the scale. And the reading on the scale will simply be the resultant upward force. The resultant upward force. So in this case, we are going to have, again, this body will again be exerting some weight on that lift. So we'll have the weight which is given by mass times the gravitational force. And again, as a result, again, there is the reaction force. We also have the reaction force, which is given by, again, mass times the gravitational force. So the body is moving upwards. That's the body moving upwards. So we have the acceleration, which is positive, and we have the weight. And we want to know what will be the reading on the scale. So in this case, again, we'll move ahead and calculate. And therefore, the resultant upward force, we want to get the resultant upward force for this body. The resultant upward force, therefore, we are going to have the upward force, and because weight is acting on the opposite direction, is like it is resisting the motion, we'll have therefore the upward force, the total upward force, we subtract now the weight of the body. Because the body is moving upwards, the weight is acting downwards, and therefore we subtract the weight of that body. So the resultant upward force F will be equal to the upward force, which we can use P to denote, minus the weight. And therefore force, which is mass times the acceleration from the Newton's second law of motion, will be equal to the upward force minus the weight of the body. So when we make this the subject of the formula, that is the upward force, so we are going to have therefore is equal to ma plus mg. And therefore our upward force, or the scale we read, the scale therefore reads, we can factor out mass, then we have acceleration plus the gravitational force. So the scale we read, the scale reads mass multiplied by the sum of acceleration and the gravitational force. And this will be the reading for the scale, that is for a lift that is moving upwards with an acceleration a. So in this case where m is the mass, m is the mass in kilograms, then we have a is the acceleration in meters per square seconds, and then we have g as the gravitational force. This is the gravitational force, again in meters per square seconds. So that is now the formula that we'll be applying for the reading on the scale for a lift that is moving upwards. Then finally, number 3, we look now at a lift that is moving downwards. Lift that is moving downwards with an acceleration a. So we have now number 3, lift moving downwards. In this case, we have the lift moving downwards with an acceleration a. So the lift is moving downwards, and therefore our acceleration is negative. Our acceleration here is negative. So we want also to obtain the formula that we are going to use to get the reading on the scale, that is for a lift moving downwards with an acceleration a. So in this case, the direction is downwards. So this is what we are having. So we have the lift moving downwards. Remember again, we have the weight. They are both acting on the same direction. And therefore for this, we want to get the resultant downward force. Here we have the resultant downward force. So the resultant downward force will therefore be given by the weight of the body, will be given by the weight, that is the weight of the body. Then we subtract the downward force. We subtract the downward force so that we can get the resultant downward force, because we have it, the lift is moving downwards, and therefore the resultant downward force will be given by the weight of this body. We subtract, we have our acceleration, which is in this case is negative, so we subtract the downward force, whereby we are going to have the resultant downward force F is equal to the weight minus the downward force, whereby we can use P prime, because for the upward force we used P. So we are going to have force, which is mass times acceleration, is equal to weight, which is mg, minus the downward force. So when we make this the subject, we can take it to the other side. We'll have now the downward force will be equal to mg minus ma. And therefore we are going to factor out m, we get g minus a. And therefore when the lift is moving downwards, the scale reads mass multiplied by gravitational force minus the acceleration. Again, where m is the mass in kilograms, g is the gravitational force in meters per square seconds, and a is the acceleration again in meters per square seconds. So that will be the reading on the scale when the lift is moving downwards. When the lift is moving downwards. And I would like you to note the following. before we apply now the formulas that we have already derived, I'd like you to observe the following. So we have seen that when the lift is moving downwards, we'll have the reading as m. So our reading will be mg minus a. Now if the gravitational force is equal to, the acceleration, for example, this body is moving downwards, the lift is moving downwards at an acceleration, let's say, of 9.8 meters per square seconds, and also the gravitational force is 9.8 meters per square seconds. It means that therefore the weight will be m is equal to g minus g, and because they are the same, we'll have 0, and therefore the weight will be 0. The body will experience weightlessness. So this body, the body experiences weightlessness as it moves downwards. So this is a case whereby the acceleration is equal to the gravitational force. Then again, I also want you to note the following. Also, if the body or if the lift is moving at a constant, velocity, if we talk of a constant velocity, the velocity is not changing, and therefore it simply means that the acceleration will be 0. If the lift is moving at a constant velocity, then the acceleration is equal to 0. And therefore, the scale reading therefore will be, we have P prime, which will be equal to mass g minus a. We are going now to have mass, our g minus 0. And therefore, the scale will read the weight of that body. So the scale reading will simply be the weight of the body. That is when the body is moving at the constant velocity. The acceleration is 0, and therefore the body will, the scale reading will be the weight of that body. That is for the case either when the lift is moving upwards or when the lift is moving downwards. Therefore, we are going to have the reading being the weight, which is mass times the gravitational force. Just to do a summary on what we have just discussed, that one, we can have a lift when the lift is at rest. When it is at rest, we have seen that the reading will simply be the weight of that body. Then we have also looked at when the lift is moving upwards, with an acceleration a. We have seen that the reading on the scale will be given by mass, gravitational force plus the acceleration. Then again, when the lift is moving downwards, with an acceleration a, we are therefore going to have the reading being mass multiplied by the gravitational force minus the acceleration. Then also we have seen that we have also seen that if A is equal to G, then the body experiences weightlessness. Then again we have seen if the body is moving at a constant, if there is movement, if the body is moving at a constant velocity, we have seen therefore acceleration is 0 meters per square seconds, and therefore it means that the reading on the scale will show the weight of that body. So these are the 1, 2, 3, 4, 5 points that you need to take note of to be able to answer any question that you may be given. So I'd like us to do one example on the Newton's third law of motion, whereby we are saying that for every action there is an equal and opposite reaction. So again, we are still in Newton's third law of motion. So I want us to do this question together. So example number 1, we have a body of mass 4 kilograms is attached to the hook of a spring balance hanging from the roof of a lift, and the question is, what is the reading on the spring balance? What is the reading on the spring balance when the lift is, then we have part A of the question, ascending, when the lift is ascending at an acceleration, when it is ascending at an acceleration of 0.3 meters per square seconds. Then number B, when it is descending, in this case now when it is descending at an acceleration of 0.2 meters per square seconds. And finally C, when it is ascending at a constant velocity. And we have been given that the value of G is equal to 10 meters per square seconds. So I'd like us to solve that question together. We are given a body of mass 4 kilograms is attached to the hook of a spring balance hanging from the roof of a lift. So we have a spring balance in a lift. What is the reading of the spring balance when the lift is A, ascending at an acceleration of 0.3 meters per square seconds? So in this case again, we are simply being asked what is the reading of the scale. Our scale here is the scale in the spring balance. One, when the lift is ascending. So when it is ascending, simply it is when the lift is moving upwards. To ascend is to move upwards. And therefore, when we want to get the reading, we simply come and apply the formula for the lift moving upwards. And therefore, the reading will be equal to mass gravitational force plus the acceleration. The mass is 4 kilograms. So we have 4 kilograms. Then we have the gravitational force, which is 10 meters per second square. Then plus acceleration, and the acceleration we have been given as 0.3 meters per square seconds. And therefore, the reading will be 4 multiplied by 10.3. And that will give us the reading on the scale. So we are going to have 10.3 multiplied by 4, which is 41.2 newtons. 41.2 newtons. And that will now be the reading. That will be the reading of the spring balance. That will be the weight. That will be the force that will be recorded by the spring balance when the lift is ascending. Then when it is descending at this acceleration, we consider now the lift moving downwards. So we are going to have therefore mass, gravitational force minus acceleration. Our mass again is 4 kilograms. Then our gravitational force is 10 meters per square seconds. Our acceleration we've been given as 0.2 meters per square seconds. So we end up getting 4 multiplied by, this will be 9.8. So we end up getting the weight in that spring balance is 4 multiplied by 9.8, which is 39.2. So we get 39.2 newtons. That is when it is moving downwards. You can see when it is moving upwards, you can see that the weight here is more than the weight of that body, because the weight here is 4 times 10, which is 40. There we have 41.2. So we have some, no wonder someone will experience some force or some pressure exerted on the foot or on the feet. That is when he or she is standing on a lift that is moving upwards. Then we have ascending at a constant velocity. We have seen that if it is moving, a body or a lift is moving at a constant velocity, when the lift is moving at a constant velocity, therefore the reading will simply be the weight of that body, and therefore the reading therefore will simply be mass times gravitational force. So we'll have 4 kilograms multiplied by the gravitational force, which is 10 meters per square seconds. We end up getting 40 newtons. That is when it is moving at a constant velocity. So that is what we have for the Newton's third law of motion. For every action, there is an equal and opposite reaction. Then we have also been able to derive formulas whereby when we have a lift at rest, when we have lift ascending, and when we have a lift that is descending. Then also we have seen that when the acceleration is equal to gravitational force, the body will experience weightlessness. And we are also saying that if the lift is moving at a constant velocity, the reading on the scale will simply be equal to the weight of that body. So these are the formulas that you are supposed to employ, especially in solutions of any question under the Newton's third law of motion. I would like to give you an exercise on what we've covered. Exercise. The first question, of course, will be state the Newton's third law of motion. State the Newton's third law of motion. That is number 1. Then number 2, you will use now that law. Number 2, use the law to explain. Use the law to explain the following. Number 1, the motion. Use it to explain the motion of a rowing boat. Motion of a rowing boat when the occupant jumps onto a riverbank. You explain what happens to the motion of the rowing boat. Then number 2, you will also explain the difficulty using the Newton's third law of motion, difficulty in walking on a sandy shore. On a sandy shore, there is difficulty in walking in such a place. Then question number 3, we have 3 women of average mass 60 kilograms are standing. They are standing in a lift. They are standing in a lift. The question is, find the reaction force of the lift. Find the reaction force of the lift floor when it is, so of course we have when it is ascending, again when it is descending. So part 1 of that question, when it is at rest, then number 2 as accelerating, when it is accelerating at 3 meters per square seconds. Number 3, when it is decelerating, when the lift is decelerating at 3 meters per square seconds. And finally, number 4, when it is moving at a constant velocity, when it is moving at a constant velocity of 5 meters per second. So you need to calculate that for the Newton's third law of motion, and again the value of gravitational force is 10 meters per square seconds. So ensure that you are able to answer those questions, and you can also do more others from the Newton's third law of motion. So during the next lesson, now that we are done with the laws of motion, we shall now be looking at the law of conservation of linear momentum. Thank you. Let us meet during the next lesson.